Now we'll see what part critical values play in the confidence interval estimate of the proportion. So recall what we mean by a critical value. That's the z-score on the borderline, separating sample statistics that are likely to occur from those that are unlikely to occur. Remember, sample statistics. We're here talking about the proportion. We'll also be talking about the mean. Those are what we mean by the statistics, the p-hat, x-bar. So calculating and getting a sample statistic that was likely to occur from one that was unlikely to occur. And this takes us back to that rare event rule where we say the probability of this occurring was very unlikely by chance, so therefore we draw certain conclusions. Remember, our assumption is wrong, or the probability that we would get this particular proportion is pretty high, and so it was likely to occur, and so we don't change anything about our assumption. Our assumption seems to be fine. So this takes us back to that rare event rule when we start talking about critical values. Okay, so critical values are based on these following observations. Under certain conditions, the sampling distribution of sample proportions can be approximated by a normal distribution. And remember, we've talked about the sampling distribution of the sample mean, sampling distribution of sample proportions. The mean and the proportion are both unbiased estimators of their population parameters. Okay? A z-score associated with a sample proportion has a probability of alpha over 2 of falling in the right tail. And we'll get some drawings of this in just a minute for a better understanding. But that cutoff is alpha over 2 on the right end. Remember, we take our alpha and divide it by 2. So the right tail has alpha over 2 in the area on the right tail, and alpha over 2 in the area in the left tail. The z-score separating the right tail region is commonly denoted by z alpha over 2, we've been talking about that, and is referred to as a critical value because it's on the borderline, separating z-scores from sample proportions that are likely to occur from those that are unlikely to occur. So let's get an idea of what that would look like. Let's see. Okay, so we're talking about approximating this with the normal curve, and the standard normal, here's our z scale, and at the mean z is equal to 0, and then in the right tail, this area here is alpha over 2, and this z-score is z alpha over 2, and that's the area in the right tail. And then the other half of that would be here. These are the statistics in the z-scores that fall in this area or down here are those that are unlikely to occur. So this is the other tail with area of alpha over 2, and it will be the opposite of whatever this critical value is. So if this one we've seen, for example, 1.96 when alpha is 0.05, then this one would be negative 1.96. Okay? So let's calculate the critical values for the three most common confidence levels. Okay, so we have, let's start with the confidence level of 90%. So when we hear that, we know that we mean, well, then alpha equals 0.10, remember, because the confidence level is the complement of alpha. So this is 1 minus alpha, and then we've written it here as a percent. Okay, so now we want to find the critical value. So z alpha over 2 would be equal to z 0.10 over 2, or dividing that 0.05. And remember, that's area to the right, and when we find z-scores we're using our inverse norm function, but remember we have to put in area to the left, and it will calculate that if you just say 1 minus 0.05, or you can subtract and put in 0.95, whichever you like, and we get 1.64485, and this is typically rounded, and your book shows this to 1.645. So this is a common confidence level. So this is the common critical value. A 90% confidence level, this is always going to be the critical value then on the normal curve. So let's see, we'll sketch that right here. So here z equals 0, and here I have 0.05 of the area, and down here the other 0.05 that makes up my alpha of 0.10, and this z-score is 1.645, and this z-score negative 1.645. These are critical values. They separate the z-scores, and recall we changed values to z-scores, so they separate the z-scores or the statistic from those that are unlikely to occur in the shaded region from those that are likely to occur here in between. Okay, so that was the confidence level of 90%. This is, again, always going to have this critical value, 90%, 1.645. Okay, let's look at 95%. Okay, this time alpha equals 0.05, right? Because 1 minus 0.05 gives us 0.95. Just want to be sure I kind of cover things the same way. All right, so our critical value, z alpha over 2, would be 0.05 over 2, would be 0.025. This is one we've calculated before. Inverse norm, area to the left, would be 1 minus 0.025, or 0.975, and here we got 1.96. That was a rounded, it was so close to 0.96 that they just take this one to 2 decimal places. It was 1.95996, and that rounded to 1.96. Okay, so let's look at that diagram. So now our area in the right tail is half of our alpha, or 0.025, and in the left tail 0.025, the sum of that is our alpha, 0.05. Here we have 1.96, here we have negative 1.96. We said this is the most common confidence level that's used. Notice this is z-scores, the number of standard deviations away from the mean, right? This is almost 2 and almost negative 2. So remember, we've talked about usual values being plus or minus 2 standard deviations. That 95% confidence level here continues with that same thought of 2 standard deviations, within 2 standard deviations of the mean, 1.96 and negative 1.96. So, you know, that's the one that is most common. Okay, but let's look at the last one, the confidence level of 99%. Okay, so here alpha equals 0.01, z alpha over 2 equals z, 0.01 divided by 2, or z of 0.005. Okay, so finding the z, we use inverse norm, area to the left, 1 minus 0.005, and that calculation yields 2.57583, or approximately what's often used, even though it doesn't seem to round this way, but what we usually see is 2.575. That's kind of standard for this one. So let's look at the diagram. Now our area here, 0.005, and down here the other 0.005. This is 2.575 and negative 2.575. The critical value, the z-score that separates what the statistics that are likely to occur, which are in the non-shaded area, likely to occur, from those that are unlikely to occur. Anything way out here or way down here, unlikely to occur. Now again, these were the common confidence levels. You could do this for any value of alpha. If you're asked to calculate the critical value for confidence level of 94%, then alpha is 0.06, alpha over 2 is 0.05, 0.03. You just put in 1 minus 0.03 here, you get a different z-score. Okay? I just did this for you for these three, but you may encounter a homework problem that asks you to find the z-score for a different confidence level other than these three. But it's the same procedure.